Hi folks, so we're getting into a new chapter which involves polynomials and so forth. But before we look at polynomials, we first need to check out power functions, and that's what this class example sheet is designed to do. The reason for that, as you will see later, is that power functions are what make up polynomials. So we need to know something about power functions before we get to polynomials. So let's go ahead and get into it. So I'm going to talk about some of the problems you'll see on this sheet and should help you with completing everything on it. As you can see, pretty much as long as we can write a function in this form where it's a constant number times the variable, can be x or whatever your independent variable is, then raised to a constant exponent. If you can write a function that way, then it's going to be a power function. Okay, the exponent that's on the variable is a lot of times referred to the degree of the power function, but that's only if that exponent is a whole number, which is most of the time what we're going to deal with in this chapter. So that's a good thing. So here's some examples of power functions, right? 2x to the fifth. That's very typical of what we might see in our work in this chapter. But you can get a little fancier. I mean, it can be any constant. So root 3 is a constant, right? 2.74 is a constant. So we don't have to have whole number exponents. We don't have to have whole number coefficients, right? That's what we call the number multiplying the x. It's a coefficient. All right, and then here's another example of where we could have a fraction for the coefficient. We could also have a fraction for the exponent. Okay. So all 6 examples in number 1, you're looking at 3 of them, are power functions. So your job is to figure out what is the k and what's the p. Okay, some of these may be easier than others. Certainly with part A, I think I'll withhold what I'm going to say about that till later, give you a chance to figure out what k and p are for that. With letter C here, I'll just point out, we can rewrite this as pi times x raised to some exponent. So I'm going to let you figure out what that exponent would be. Okay, but your k would be pi here. For letter E, let's just think real quickly, what is the exponent on x here if you have a square root? Yes, so the square root, right, is the 1/2 power, right? A cube root would be 1/3, fourth root 1/4. So this is x cubed divided by x to the 1/2, and that can be written as x raised to some power. All right, I'll let you figure out what that's going to be. All right, so why don't you pause the video and try these 3. I know the numbering is weird. Usually I go across A, B, C, but this time the computer decided to do something different and I didn't catch it. All right, so pause the video and see if you can finish these. Remembering each time you need to say what k is and what p is for each of these. All right. Let's move to the next page and I'll give you some hints for those 3. I really don't think I'll say too much about these 3 problems, except for the fact that they can all be written as a constant times x raised to an exponent. And some of it might require some simplification. Even letter F over here, even though you don't see an x, there we can write it as 2 times x. You just got to figure out what power would essentially show up as being just like 2 times 1, right? Because that's what 2 is. The idea behind number 2 is really just to pick up on the patterns between when you have, an odd whole number versus an even whole number for power functions. So these 8 graphs you should be able to go through pretty quickly. Of course, you should already know what, y equals x is, y equals x squared, y equals x cubed, and then find the pattern that works for the rest of them. The idea would be if you were to see the power function y equal to x to the 67th power, you would know pretty much what it looks like. For the ones here in number 3 now, you've already established kind of what the pattern is for the graphs according to their exponents. Now pay more attention to the coefficients here and react accordingly as to whether it's positive or negative for your graphs. Like we were doing in number 2 now, in number 4 we want to basically establish a pattern in the graphs where you have negative integers on your power functions. So perhaps you already know what these graphs look like. Of course, x to the negative 1 is the same thing as 1 over x. So you may remember what that graph is like. If you need to, I guess you could make a little table if you wanted to. Certainly, let's see, if we plug in 1, I believe we're going to get back 1. So let me use a different color here. So I know I'm going to get back 1, 1, which by the way is true about any power function whose coefficient is 1. It will go through the point 1, 1. And of course, as we plug in numbers like 2 and 3, we're going to be getting smaller and smaller fractions, right? We're going to be getting 1/2 and then 1/3, 1/4. And we can kind of see, right, as x gets bigger and bigger, our number's getting smaller. Now, what's going to happen if we plug in, 1/2? We're just looking for the reciprocal, right, of these numbers. That's what 1 over x will do. And of course, that would give us 2 when we plug in 1/2. So we'd be up here, using a different color inside here. If I plug in 1/3, which is even closer to 0, we're going to get even higher. So I think we can see this pattern, right? That we've got this graph coming down here like this, right? And if we plug in 0, of course, we've got 1 over 0 that's undefined. So hopefully you're already suspecting that there's a vertical asymptote at 0, right? And now when we plug in negative numbers, like -1, we're just going to be having the same thing happening on the negative side, right? We'll get -1 down here, and as our x values get bigger and bigger in the negative direction, we're going to have smaller and smaller negative numbers for the outputs, and so forth. So, so the other side of this, right, is a graph that looks like this, all right? And this is basically, a lot of times we'll say this is the basic hyperbola. That's what it is. It is a hyperbola that you studied maybe last year in Algebra 2. It's got a vertical asymptote. It's also got a horizontal asymptote, and the curve conforms to those two asymptotes. Kind of sits across from each other. All right. I'm going to leave it up to you, though, now to figure out what's going on when it's -2. Just keep in mind now, all these negatives that we were plugging in are basically going to become positive, right? So you're probably not going to end up with any points down here in the bottom half of our graph here. Now keep in mind, I'm just looking for the basic shape of the graph, so you don't necessarily have to have all these little marks on your graph. It's more like what you were doing number 2. We just want to see what's the basic shape over here for x to the -2. And then there should be a pattern that you start to establish when it's -3, -4, and so forth. When you get to ones like letters E and F, hopefully the pattern is established between having an odd negative integer and an even one. But now you got to pay attention to the coefficient, right? And pay attention whether it's positive or negative. That, of course, can also affect the graph. One last thing I wanted to touch on was something to do with maybe fractional exponents here. We haven't dealt so far with things like x to the 1/2 or x to the 1/3. I think you guys know those would be your root graphs, and probably already have an idea what the square root graph looks like, or hopefully the cube root graph. But basically, what is the difference if your exponent is less than 1 versus whether your exponent's greater than 1? Perhaps the best way to keep them straight is to think about what does the graph look like when your exponent equals 1. Of course, we know that when the exponent equals 1, we get a line, such as y equals 5x to the first. So we just know it's straight. It's going through the origin, right? Because when x is 0, y is 0. So all we have to do is think about, all right, what if it was 5x squared, something bigger than 1? We know that, right, would curl up. right? And then if it was something like 5x to the 1/2, something less than 1, it would basically curl down. And that's really all you have to keep in mind, that if if your exponent is less than 1, it's going to be concave down coming out of the origin. And if your exponent is greater than 1, it's going to be concave up coming out of the origin. So if you can keep that straight, that's half the battle. Hopefully this class example sheet has given you enough to work with as we move forward into polynomials and rational functions. Understanding these graphs of the power functions is very important. We will come back to them both when we're dealing with polynomials as well as when we get to rational functions.